So about 2.5 years ago, I found myself in a room with 4 other engineers at Skyscanner, and we were tasked with answering a question that I thought should be fairly simple to answer. And that question was, where does our company's revenue come from? As it turned out, it wasn't quite that easy to answer. But the reason we had this question in the first place was we now had to comply with regulations known as SOX. It's in the US, it stands for Sarbanes-Oxley. And it essentially meant that we needed to be able to show for every line in our financial statements and our records, every line there was traceable and that we could prove that the data there was reliable and from reliable sources, and that it couldn't have been altered in any fundamental way by anyone inside or outside our company. And in this case, like I said, it wasn't that easy to answer. Like, we were scribbling on whiteboards, trolling through GitHub, asking questions to other teams, trying to figure out how does revenue actually flow through our streaming pipeline. And it actually took us a couple of weeks to get enough confidence in the answer to give a recommendation to say, yeah, this is exactly how we're going to secure it, and this is how we're going to make sure that these numbers don't get fundamentally changed. And it gave me quite a bit of pause. Like, how did we end up in this situation where no one individual or one team even could tell from beginning to end, from producer all the way to financial statements, like how the data flowed and what was happening in there? So what I'd like to do today is share a story with you of how the data platform at Skyscanner evolved over time, from batch to streaming and to both. And by sharing these stories, I hope to share some of the lessons and help you avoid some of the traps that we fell into along this journey, doing things in a fairly agile fashion as we did. Now, when I originally submitted this talk, the title was From Batch to Streaming to Both. And in the weeks following, I've been rethinking it and thought that a more accurate title might in fact be From Batch to Streaming to Both, and then back again, perhaps. And I'll get into why there's a question mark at the end there, and this new title wasn't quite as catchy, so I didn't change it. But just to give you some idea of where we're going and the kind of thing I'll be talking about later on. My name is Herman, like Nikki said. I work at Skyscanner. If you haven't heard of Skyscanner, we help you plan trips, and we do that by helping you find the best flights from A to B. When you get to B, you can also find good accommodation and car hire and all these things. And when I say good flight, that might actually differ depending on the person. That might mean cheapest. It might mean lowest carbon footprint. It might mean most comfortable. And we allow you to search across all these different things. And over the years, we've grown to be fairly popular. So it's about, at peak, we have about 100 million monthly active users. It's available in 30+ languages. We've had 100 million or more app downloads. And we have about 1,200 partners, by which I mean online travel agents and airlines and hotels and so on. So fairly big. And with that scale comes also a pretty big data platform. Now, what I'm showing you here is the number of messages per second that we were processing from 2016 to fairly recently in our streaming data platform. Now, our platform wasn't always streaming, so this isn't the full timeline, but back in 2016, we were doing about 20,000 messages per second, later the year about 80,000 messages per second, and that grew to about 2 million messages per second now. And that's fairly big scale. To put that into perspective, it's about 172 billion events per day. It would be several petabytes if we stored everything, which we don't. But even if you stored it in an efficient format like Parquet, it would be quite a lot of data. Now, our story started with a batch pipeline, like I alluded to. And like many organizations, something you're probably familiar with, we started with data being in lots of disparate sources. We had Mixpanel, we had Google Analytics, we had an OLAP database that we lovingly refer to as the Cube. And This cube allowed you to do slice and dice queries fairly effectively and efficiently, but it was hosted on-premise because we had not yet transitioned to the cloud. And we were running into some scaling problems. Like, firstly, we didn't really want to wait 24 hours for batch extracts to happen. And as we started processing more and more and more messages, the cube was starting to show its age. And so, together with a transition to the cloud and AWS, we started moving and exploring the possibilities of a streaming data pipeline. So we went from batch to streaming, and we didn't really know whether this whole streaming thing was actually going to catch on. We put Kafka in the middle. Kafka looked like a really promising technology at the time. And we said, all right, on the producer side, we'll have our servers communicating directly with Kafka, writing messages there, and we'll have an HTTP API which we can use for web clients and mobile clients. They can write to that instead using REST and JSON. And this HTTP API would convert the JSON to protobuf. So pretty early on, we had this convention that all topics in Kafka should be protobuf. This was a really good thing. If you're not using something like protobuf as a message format, like Avro or Thrift or any other number of ones, if you're not using a binary format like that, I really recommend you go out and do that. And we'll see some of the benefits later in this talk. But an interesting thing here is that we used our Kafka cluster for 3 very different kinds of data as well. So we had metrics, we had business events, and we had application logs. Metrics would be pulled from Kafka and delivered to OpenTSDB, which is a very scalable time series database based on HBase. And our data platform users would be able to query that through Grafana. Then business events, that would go to S3 as Parquet and be queryable through systems like Athena or Redshift or any number of engines that we later added. And application logs would be sent to Elasticsearch, and our customers within Skyscanner, the engineers, would be able to query their application logs in Kibana. And I just want to say that this is still a good design, in my opinion. I think it's fundamentally a really good thing to do, because it's sort of paradoxically both decoupled and unified. It's decoupled in the sense that the producers no longer need to know which consumers are going to be interested in the data. They could just produce to Kafka and kind of forget about it. That's good. And the consumers similarly don't need to know exactly who produced the data. And you don't have this web of interactions that you might have if all the consumers need to be aware of the producers and vice versa. So it's decoupled. That's a good thing. But it's simultaneously unified in the sense that all the messages now have to go through Kafka. And Kafka becomes, to some extent, your single source of truth. And in fact, around that time, we started talking about this concept of the single unified log, which basically just means that all the messages would now go through Kafka. If you had a question, you could answer it from Kafka using the data in Kafka. And all the other systems would derive their truth from Kafka, from this single unified log. Now, this was all good. Our users really liked it. But pretty soon, they were telling us, hey, you know what? What we'd really like to do is add some transformations to the topics that we have in Kafka now. We would like to merge topics. We'd like to split them into only the information that we care about, or we'd like to enrich them with further information from other APIs. And we said, that's great. This is exactly what we think stream processing is for. And we wanted to exercise a little bit of control, though. We didn't want everyone to reinvent the wheel and build their own stream processing system. So we standardized on Samza, Apache Samza. If you haven't heard of this, you can also think of Storm. Apache Storm is another similar one. We standardized in Samza, and we basically made a templated version of this that any team in Skyscanner could easily create within a couple of clicks. By filling out 2 very simple Java functions, you could have a stream processor up and running within minutes. And fairly soon, we had hundreds of these Samza jobs running. And they could do any kind of transformation. We didn't put any limits on that. And things were great. We were pretty happy. There was one problem, however, that we found also fairly early on, which was that as we were transitioning to the cloud, we had some services that had hundreds of containers, and when they did a blue-green deploy, that would suddenly add hundreds of new connections to the Kafka cluster. That would then have a cascading effect of lots of extra metadata on the cluster and would cause some temporary degradation. And we decided that for that reason, mainly, we would make sure that the servers within Skyscanner that are now deployed to AWS would also talk through this HTTP API to Kafka. So they weren't talking to Kafka directly anymore. And this was a really, really good move in retrospect, because it actually allowed us to decouple the production from Kafka itself, which means we now have a place we could implement any kind of business logic. So we could enforce the usage of protobuf rather than have it as a convention. We could check that certain fields are set. We can make sure that messages are good enough quality to go in, all these things. And also some other surprising benefits, like we could have this API deployed in multiple regions, whereas our Kafka cluster was only deployed in one region at the time. And this API would be in multiple regions. We could have local syncs that we write the data to, and then forward the data onto our Kafka cluster, the central one, which means that write resiliency is a lot higher. Even if our central Kafka cluster was having an issue, we would not lose messages. We would still be able to take those, whether from server-side or from mobile devices or from the web. So this proxy was a really great move. And we felt like we were in a pretty good place. But then we realized that maybe we have become the victims of our own success to some extent. So we now had about 100,000 messages per second going through the platform. And it was in this room where we were trying to trace our revenue events that we saw that actually these revenue events were going through an epic journey. So first, they would go from the server to the HTTP API. That's all easy enough. Then to Kafka. That's all as we expected. Then a SAMSA job would pick that up. It'll pick up this revenue event. It might add some extra information, something like device information extracted from the user agent, for example. OK, that's good. Then another SAMSA job would read from this second topic and write out to a third topic. And in this case, it might add some information like geolocation information. And as we started tracing it, we realized there was a third SAMSA job writing to a fourth topic, and a fourth job, and a fifth. And so it went on, long, epic journey, all the way until finally the final SAMSA job, number of hops later. At this point, we probably needed a SAMSA job to do some deduplication, because as you know, distributed systems introduce duplicates pretty easily. So before we commit the final results that we will use in our reports to S3, we have a deduplication job in there as well. This was fairly complicated. And so the first lesson that I want to share is that Conway's Law is true for data platforms. Now, if you haven't heard Conway's Law before, it basically says that organizations which design systems are constrained to produce designs which are copies of their communication structures. And here I've substituted systems for data platforms, because I think the same thing goes for data platforms in particular. And when we were looking at our revenue events in this case, we realized that all these different hops, all these different SAMSA jobs, basically mirrored all the different organizational hops that the data had to go through. And to understand this, it helps to give a little bit of context about how Skyscanner is structured. We operate using a squads and tribes model, which basically means we have very small, 6 to 7 people autonomous teams, and they solve problems in an independent way. They try not to have too many dependencies. And so what happened was, for example, the producers would produce the data. It wasn't in their interest really to make sure it made it all the way through. They didn't have the full picture. Similarly, other teams would create SAMSA jobs, enrich the data, write it back, and so forth, all the way through to the financial reports. But no one single team had the full picture. So Conway's Law is true. And we perhaps didn't realize this enough early on. But one thing we did say was that we're a small platform team. We're trying to do the stream processing thing for quite a large company, and we're trying to make that platform as self-serve as possible. And I still think being self-serve is very good. It basically means we enable our customers as data platform users to use our platform without us needing to get involved, without us needing to have deep knowledge of every single data set. Because as a small platform team, you just can't do that. What we didn't realize, though, was that metadata then becomes absolutely critical. And it was metadata to some extent that we lacked when we were looking at the pipeline and trying to figure out how events flow through the system. So let's talk about metadata. You may have noticed, if you were very eagle-eyed in the architecture diagram I showed earlier, that there was no schema registry in that diagram. So how did consumers know which schema to use, and how did producers tell consumers which schema to use? And the answer to that, in Skyscanner's case at least, is convention. We had a simple convention for topic names, and every topic at Skyscanner looks like this. It's like prod or sandbox or local, so the environment name, and then a dot, and a service name, dot, event name, dot, schema, dot, message. So this tells you from a glance which schema was used, and we store all the schemas in a central repository where everyone has access to it, and you can easily see, okay, this is the schema and the schema file name and the message, and go look it up in that repository. And this was a pretty good convention because it actually allowed us as a small platform team to share quite a bit of data about each topic and know how to interpret the data in that topic without us needing to go build an API to support this. Nowadays, Confluence schema registry might actually do the same thing. However, until recently, I believe it at least didn't support protobuf. Back when we built this, the schema registry didn't exist. So pretty soon we had topics looking like this: prod.identityservice.audit.identity.audit message. That's fairly good. Tells you what it is and what schema to use when you read it. We also had topics like prod.flyingcircus.applog.applog.message, which is less useful, but it came down to the team how useful they want to make these topic names and how much context they want to give in it. And it was a very useful thing. Now I want to distinguish here between three different types of metadata: descriptive, structural, administrative. With descriptive metadata, you're answering questions like, what does this data set mean? Who owns it? What does it contain? Where does it come from? Structural metadata is more about how does this relate to other data sets? How is it organized? How is this data set sorted and partitioned? And administrative, which is about how far does this data set date back? How frequently is it updated? How large is it? How complete is it? And all three kinds are very important. When we started looking into it, we had some descriptive metadata by virtue of using protobuf and by having our topic naming convention. That was good. We had some structural metadata, but we didn't know, not without a lot of effort at least, how data sets relate to one another. This was something we missed. And we could tell if customers were to ask us how something was partitioned, we could go and look that up, but it wasn't easy for our customers to tell that. And then administrative metadata, we didn't have much of it at all. Similarly, we could go look it up if someone asked with a fair bit of trouble, but we didn't surface this to our customers, and we didn't have a lot of visibility into this ourselves. So the second lesson is that metadata is critical, especially when you're building a self-serve platform that you want a lot of people to use in your organization. And especially the relationships between data sets. Like if we had this information, determining the revenue pipeline and determining where our revenue came from would have been a lot easier. And ideally, of course, it would be automated, and ideally we'd have all this from the start, but we didn't. So we did the next best thing, which was we started to gather this information manually. When users wanted to archive something to S3, we asked them, could you please use your knowledge of this system to tell us what is the hierarchy and how do events actually flow to make it all the way to the final topic that you now want to commit to S3. And that was a start. It gave us some form of metadata. We did it knowing that this would get out of date, and it would be better if this was automated. But a bit of metadata is already better than not at all. And like I mentioned, the tools like schema registry are a start here, but they're not the full solution. You need to also think about how you can make these relationships between data sets and the 3 different types of metadata we just talked about, make those visible as well. Now, many of you have probably seen this picture before. It's from an XATD comic, and it shows the flow of characters through Jurassic Park. And I like to compare this to topics flowing through Kafka. So just to explain this diagram briefly, on the x-axis we have time, and on the y-axis we have the proximity of different characters to one another. So if the characters are in the same scene, then the lines are close together, and if they're far apart geographically, then the lines are further apart. And as you might expect in Jurassic Park, some characters make it all the way through, some characters don't make it all the way through. And the reason I'm saying this is a bit like a Kafka cluster is that topics. So where were we? Jurassic Park. We thought this was what our pipeline looked like. It looked a bit more like the movie Primer, which I don't know if everyone's seen it. It's a good movie. Go and watch it. So when we started looking into it, things were pretty difficult to follow. That's kind of the point here. And data engineers control the plot line. And by this I mean that when you design the system, the restrictions you put in place on your data platform users kind of determine the plot line you're going to get, determines whether you're going to get Primer or 12 Angry Men. Both very good movies. If you haven't watched them, I recommend you go and watch them. But if I had to choose a plot line for my platform, I would rather have a plot like 12 Angry Men than Primer. And so that's kind of what we did. We realized that these SAMSA jobs, these stream processing jobs, they were causing us a bit of pain because they were the thing that, firstly, we didn't enforce using protobuf there, for example, but we trusted people would use protobuf. But more to the point, we couldn't really trace the lineage through SAMSA. We didn't have a lot of control because it was essentially free code and people could do in them whatever they wanted. This made it pretty difficult to trace things through the system. So what if we could just go straight from the HTTP API to S3? This would also avoid a problem that we had with SAMSA jobs in terms of repeatability. So when things go wrong in your streaming pipeline, it's really worth thinking about what you're going to do in that situation. For example, if a SAMSA job stopped, then it would affect all the downstream SAMSA jobs. And users would come to us and ask, what happened? Where did my data go? Which team do I talk to? And another problem here is that when you inevitably do discover a bug in your SAMSA stream processor long after the fact, it's very difficult to go and fix it. You basically have to do a replay. You have to send that data through the SAMSA job again. And that would have unpredictable consequences, again, on the downstream SAMSA jobs if you don't have a good handle on what's happening in them. So what if we could go straight from this HTTP API that we introduced straight to S3? A bit less like Primer, but more like 12 Angry Men. So that's kind of what we did. We said, we're going to still have Kafka. We're going to send all our metrics and application logs and even business events. Everything we were sending there before, we're still going to send to Kafka. And that will still be going through stream processing, all the usual things. But in parallel, we're going to also send it to Kinesis. Now, AWS Kinesis, it's a managed service that AWS offers. It's a bit like Kafka. We chose it not for any big technical reason other than it's very easy to spin up in multiple regions, and AWS pretty much manages it for us. So we chose Kinesis here, and we started sending things to Kinesis and then reading them from Flink. Flink is another stateful stream processor. And using Flink, we could kind of abstract away, firstly, whether it's Kafka or Kinesis. It has adapters for both. And then send those messages to S3 every couple of minutes. So it would batch them together into a bigger file, into a Parquet file, and then send it to S3. But this time we also learned a lesson. And we said that, OK, of course, we still need transformations. We can't completely do away with them. Transformations are useful. Data sets aren't in their final form the moment they're produced. So we allowed transformations to be done, but this time only in the archive and only in a repeatable way. It meant that we wouldn't need to do any kind of replay anymore. We could just read that day's data with our Spark job, for example, to do the transformation again and write the data again. And it wouldn't necessarily need to have an impact on any other jobs. But we also realized that we need to make sure that these Spark jobs that do these transformations on the archive have to at least register their dependencies and register where they're going to write, so that when we do find errors and we do correct them, that we know what we need to do to correct it in the downstream systems as well. This was really important. We also decided that this is a good opportunity for us to measure completeness and tell our users, give them a bit more metadata about the data sets that they're working with, and tell them that, yeah, all the data that we found in our HTTP API has been delivered to S3, and all the transformations you were expecting to be done have been done. We can verify that for you as a platform. So lesson 4 here is that repeatability is very important. Repeatability is something that is not always discussed, and it's more of a failure case in some cases for streaming platforms. And it seems like streams often have to choose between replays and accepting errors as permanent. And replays can be really complicated. In our revenue pipeline example, we had about a 30-step process for doing replays. They were really, really complicated, and we didn't have a lot of confidence in doing them because you don't do them very often. So if you can avoid them entirely, that might be better, and that's sort of the approach we went with here. Might not work in every case, but we found that to be a bit simpler. Batch processing is good because it can be done again anytime. The source data is always there. It's a bit easier to manage. And going straight to the archive in small batches, you could say micro batches, sort of gets you the benefits of both. You still have fairly low latency, but your replays can be at least quite a bit simpler. Now, some of you familiar with data architectures may be asking, is this a Lambda architecture? Is this what you're telling me about, Herman? And yes, it is. For those of you who haven't heard this term, I just want to make clear that Lambda architecture here, it doesn't have anything to do with AWS Lambda or Lambda functions. I believe the name derives from the fact that the Lambda character in Greek has 2 little legs that you can see there. And this corresponds to the 2 legs in the data platform. There's a streaming leg and there's a batch leg. And yeah, this is sort of what we built. We had a stream processing side, and we had a batch side that we introduced now. And it's a little bit different. Like, this has been used in other companies like Yahoo and in Netflix quite successfully for a number of years. They use Lambda architectures, but they came at it from a different angle. They actually had Hadoop batch processing pipelines, and they weren't satisfied with the high latency. They weren't satisfied with the 24-hour wait they needed. And so they introduced a parallel streaming architecture. And we came at it from the other direction. We had a streaming pipeline, latency was fine, but the error case, the replays that we had to do, those were pretty complicated, and we wanted to simplify the lineage and increase our visibility over what was going on. So we added the batch pipeline. And it almost feels like this is an inevitable architecture to some extent. But then I want to question, is this really a Lambda architecture? Because what we're doing is pretty low latency on both these legs. In fact, we realized that we could write files to S3 every 5 minutes, but we could also use a technology known as Delta Lake, which is an open source technology, and use that as a sink for streaming and for batch, and as a source for streaming and for batch. So just to talk a little bit about Delta Lake, this was initially developed by a company called Databricks, and it's essentially metadata on top of Parquet in your archive. Could be HDFS, could be S3. And what it gives you is ACID-compliant features and semantics on your S3 archive. So basically, you can do updates and deletes on data in your archive. You can do very nice things like sort the data, they call it Z-ordering, which can make certain types of queries very efficient. So in our case, because of GDPR, we need to be able to look up individual users and delete their information if requested. And something like Delta Lake allows us to do this. And in our experiments, we found that using Delta Lake instead of just plain Parquet could speed up these kinds of needle in haystack queries up to 100 times. But it also does something really nice, which is it gives us the ability to roll up these very small Parquet files that we're constantly delivering into bigger files, which we know improves the query performance as well. Like from our experiments, those speed up typical queries by about 2 times, just those roll-ups. And Delta Lake is able to do these roll-ups without affecting running queries. So that's where the ACID database compliance comes in. It's really nice technology. And we put this in place in our pipeline. So we had Flink delivering files to S3. At the moment, it's delivering them as Parquet. But then we have another transformation step that loads them into Delta Lake. I'm hoping in the future these will merge into one, and we'll be writing directly to Delta Lake. But in essence, we have very low latency on both sides. We have 1 minute latency in our Kafka pipeline, and we have about 5 minutes latency right now in our so-called batch pipeline. But I think it's more appropriate to call it a micro-batch pipeline. And that's pretty much it. So I think in the future here, it seems to me like our streaming architecture that we originally started with, we had some reasons to go back to batch, but it's more like a micro-batch this time. And our micro-batch architecture, in this case, the latency is getting lower and lower. In the future, it looks like the latency could be low enough that most of the use cases we were using Kafka for before might not need to be done in Kafka anymore, and we could do this in our batch pipeline instead. And perhaps we'll only reserve Kafka for very, very real-time use cases like metrics and application logs. So the key takeaways here. I'm going to quickly go through all the points I made because I realize it's been quite a long time now. The first one I talked about was Conways Law and how that's true for data platforms. This basically means that your data platform will structure and the data in it specifically will mirror that of your organization. And so luckily for me, the advice I can give you here is going to be fairly generic because it will depend on your exact organizational layout, what this means. But it's really worth thinking about it up front and realizing that this is something you need to account for. The second thing was that metadata is absolutely critical. Like having a self-serve architecture is very good. As your organization grows, you don't want your platform team, your data platform team, to become a bottleneck for using data. And so you can't know about every data set, but that means you need to provide your users and yourself with the metadata you need to work with those data sets efficiently and make good decisions. It's as important as the data. Data engineers control the plotline. With this, I mean that the restrictions you put on the platform, there's the ways that you're allowed to use the data, that actually matters. And it determines whether you get a really complicated plotline like Primer or whether you get a pretty simple plotline like 12 Angry Men or Jurassic Park. And then I talked about repeatability and how that's important and how it's often overlooked in streaming pipelines. It's a difficult topic. Getting repeatability right, in our case, meant completely avoiding streaming. That's not necessarily the solution. Like, I think you can do repeatability with good partitioning schemes on Kafka, for example. You can achieve some of these same semantics, or by keeping your system fairly simple, then repeatability is not such a big problem. But it is very important to know what your plan is here and know how you're going to keep it under control. And then finally, I briefly touched on Delta Lake, and it's a technology that we're starting to use now at Skyscanner. We're using it right now as a bit of a batch sync and probably a batch source, but I'm hoping soon also as a streaming source, which will give our customers the ability to choose whether they want very low latency, maybe 5 minutes, maybe 1 minute, or whether they are okay with having daily batch transformations done on the archive. Either way, they can use Spark. Either way, it's the same code. And that's quite a nice thing. It's quite a nice thing to be able to do. So if you haven't heard of Delta Lake, that's a good technology to go explore next. We're already seeing quite a bit of benefit from this at Skyscanner, and I think we'll see more of that in the year to come. And if you do all of this right, all these many different things, then I hope you don't one day, like me, find yourself in a room where you have to answer the question, where does your company's revenue come from? Thank you.
Do we have any questions for Herman? Oh, there we go.
Thank you for the presentation. Have you considered introducing some lineage technologies, like Apache Atlas or IGC type of technologies?
Yeah, that's really important. That's something we're actively looking at now and deciding what the best system will be for us. So we've looked at Atlas, we've looked, interestingly, at Glue specifically, because we use Glue, that's AWS Glue, for pretty much everything. And we're thinking what we'll do is store the metadata for lineage in that, instead of using existing open source solutions, because our system is quite customized. But just having something like this, having this metadata at all is the important thing. Apache Atlas, I believe, yeah, is a good option. We will likely be using it soon, but aren't yet.
There's another one here.
Oh, yeah. The only thing I was wondering, so looking at what you were showing with your stream sort of processing, it seemed like your issue there wasn't so much batch versus stream, but it was almost the fact you had so many different dependencies in the stream engine. So you had so many teams where, one team has a little bit of data, has a new topic, the next team reads that, the next one. Yeah. I mean, how was that working with the batch one? When you changed it later to the Spark engine, were you having lots of batch jobs that all depended on each other? Or was that really what you fixed, having so many dependencies, and actually said that each team, instead of depending on the previous team, is going to kind of start from the beginning actually and add most of their own data at that point?
Yeah, we'll see how it ends up. Like this side of the pipeline is fairly new, so time will tell whether we were successful in simplifying the whole thing. But what I can say is that by having the metadata at least this time to know what the dependencies are, teams can decide whether they want to start from scratch from source or use some of the existing metadata. And you can get the picture and you can see what's available already quite a bit more easily than you could before. Like we also added some useful distinctions here in terms of the quality of the data. So we're thinking of like putting things into, let's put it into Databricks terms like bronze, silver, gold. And so you can know the quality of each data set. And we will prefer that people build their data sets on top of gold data sets so that the transformations happen in as few places as possible and not all over the place. But that's again, metadata is important to make this visible and for teams to know which data sets to build their own transformations on and not necessarily do everything that other teams have already done. Yeah, but it's a good question. Time will tell whether we were completely successful here.
Are there any more? There's one.
What was the relationship between those architectural choices and your original performance graph? And also in your Lambda with your two flows of data in the stream and in batch space, what was the split of the 2 million per second across that?
Sorry, could you repeat the question? Didn't quite hear.
So you had a performance graph that was showing your increase in rate over time. All those different architectural changes, at what points did they happen on those improvements? Were the improvements a result of the architectural choices at all? And then on your final picture with the split of metadata versus the business events, where does the 2 million per second fit across that? Is that both of those or one of them?
Okay, good question. Yeah, so the Kafka cluster right now in all the pictures is doing 2 million. Like, we haven't reduced the amount of data in Kafka at this stage. That might happen in the future. And the batch side is doing quite a bit less. I think I'm going to just estimate here about 20% of that. And in terms of how things played out in the timeline, the batch pipeline we started introducing this new batch pipeline about a year ago. And so it's been rolling out. It's kind of still in the early phases of seeing how it works, but it's processing only the business events and not the metrics and application logs. And actually, as time goes on, we're splitting these completely. We're trying to not use the same Kafka cluster for all these different data use cases because they are actually quite different and have different profiles. So what it seems like will happen is we will use one Kafka cluster for metrics, another for logs, and then probably this batch pipeline for business events only.
We're probably going to leave it there, just to give you some time to get to the next talk. So it's still going to start at 4:10. There may be some people still in the previous room, though, if they're overrunning a little bit, so just be patient, and hopefully we can start on time. But thanks so much, Herman.
Thank you.